If you've ever found yourself like this, you might have been tempted to turn on your AC.
What you may not know is that current AC methods use R410A, and it's very harmful to our environment.
Current research in global warming indicates that for every 1 pound of R410A released, it is equivalent to 2,000 pounds of carbon dioxide in the atmosphere. Our team, the Chill Innovators, has been tasked by our sponsor, Shanghai Zhixing 3D, to continue to develop a new technology known as electrocaloritic cooling. Electrocaloritic cooling, also known as EC cooling, uses a self-regenerative heat pump device to transfer heat from a heat source to a heat sink, similar to coolant moving heat from an engine to its radiator. This device is placed onto a hot material to cool it down. The flap that absorbs this heat is a piece of gold foil encasing ferroelectric polymer and carbon nanotubing. The way this works is by applying a high voltage to the foil piece to make it flick and transfer the heat to a colder material.
Our students from SJTU began our process of increasing efficiency through a series of physical tests. The first of which was deflection testing. This test involved changing the size of the SRHP device and the orientation of the flapping. The result that provided the best deflection was the pre-curved cantilever beam orientation. The second test evaluated different electrode geometries. The results displayed that either the chamfered square or circle geometry provided results that prevented any forms of irregular deformation. The final test that was completed was an infrared temperature test that provided temperature data when different voltages were applied. This test showed that as more voltage was applied, a larger temperature difference was created. Therefore, the highest voltage at 3600 volts was the most viable option moving forward. Meanwhile, the Penn State team evaluated multiple parameters of the SRHP device through a simulation software. The first parameter evaluated was the materials of both the heat source and the heat sink. Copper was the material that provided the best results by allowing temperature to dissipate at the fastest pace. The second parameter was the time step of how long the device was activated. After testing both 1 second and 2 seconds, it was evident that 2 seconds was the better parameter. The final parameter evaluated was heat flux. We concluded that at 20,000 watts per meter squared, we saw the largest energy loss and therefore the best results.